Hello guys, welcome once more back to our channel. And in this lesson of today, we'll be looking at the binomial expansion. Please don't forget to subscribe and click on the notifications button so that you'll be aware of all our newly loaded videos. Welcome, don't forget to share your videos, to leave your comments and propose other topics you'd like us to put to serve you out there. Thank you so much. So we focus on the binomial expansion. So what are binomials? Binomials are two-term expressions in which each of the terms is a monomial. When this two-term expression is raised to a power, we have a binomial which can be expanded to obtain various terms or a series. This process is called binomial expansion. Binomial expansion. So for example, here we have a monomial, this is a single term, plus a monomial, these are single terms. Now, when you bring these two together, we have a two-term expression, which when you raise the power n here, it gives us a binomial, which can be expanded to form a series. So this is what a binomial is all about. So if the power there is 2, then we have a quadratic. So let us consider the binomial shown. It can be expanded as follows. So we have a plus b to the power n, which can be expanded as follows. So to expand this, we have n, we start with this power n, then the first monomial that is inside, n combination, so we start with combination 0, n combination 0, so we always start with n combination 0, then we take the first term of this binomial, that's the monomial, we raise it to this power n, then the second term is raised to the power 0, like this. Now, for the next term from this expansion, we are going to have plus. So one very important thing to note here is that for these monomials that have been expanded here, a plus b, their powers, the sum of their powers must always be equal to n. So like here, we have n plus 0, which is equal to n. So for the next term, we are going to have n combination, the next combination now should be 1. So we now have n combination 1. Now this a to the power n is now becoming a to the power n minus 1. So the power reduces by 1. Then this power of b is increasing by 1. So in essence, what we are saying is, for these binomials, the first monomial, the power keeps on decreasing by 1, while for the second, the power keeps increasing by 1. And equally at this stage, we see that the sum of their powers here is also equal to n, because n minus 1 plus 1 is equal to n. And let's not forget, n combination 0 is the same as 1, and n combination 1 also gives us n, as we are going to see. All right, so the next one now we're going to have, of course, you already know this n combination 0, n combination 1. Therefore, the next one should be n combination 2. Instead of, we now have n to n minus 1, so the next part should be n minus 2. Then for the b's, we have 0, the next is 1, so the next should be 2. So this process continues repeatedly. We will now have n combination 3 here, a to the power n minus 3, and b to the power 3. There is one other very important thing that I want you to note. Here we have 0, look at this point, we have 0. So this is n minus 0. This part of b is 0. It corresponds to this part of this combination here. So it's n combination 0. This 0 meets or matches this 0 at this n. Here is also n minus 0. Now look at the next term. This position is 1. This position is 1. And this other position is also 1. This is one very, very important thing which we are going to see in applications when we are going to be looking for a particular term in the series. Equally here, we have 2, n minus 2, and 2 at these positions, 3, and so on. You must take note of this. So it continues until we are going to have n combination n, a to the power n minus n, that's going to give us a to the power 0, right? And b to the power n. So this is the binomial expansion. This is what it's all about. Equally, the Pascal triangle can be used to explain some aspects of this. But the Pascal triangle is limited because it is good when n is, first of all, a natural number, and secondly, when the value of n is not large, because as n becomes large, it is prone to errors. So recall that n combination r is written as n combination r, if you have not done combination. So n combination r is equal to n factorial over n factorial minus r factorial. All right, at this point, we have r at this point. Let me do the correction. So n combination r is equal to n factorial, all that on n factorial, not on n factorial, all that on r factorial. So all this on r factorial, okay? So with the correction done, n combination r is equal to n factorial, all that's on r factorial into n minus r factorial, where n belongs to the set of natural numbers, where n is an element of the set of natural numbers. And recall that the first natural number is 0, then we have 1, 2, 3, and so on. So those are the values that n takes. All right, let's look at the expansion in simple terms. So to expand a plus b to the power n, we are going to have a to the power n, all that on 0 factorial, so we can simplify it like this, plus n times a to the power n minus 1, b to the power 1, all that on 1 factorial. So look at it, so you can write it in this form. The next term should be, so this is another way of working with binomial expansion. So we have this power now n into n minus 1, a to the power n minus 2, b to the power 2, all that on 2 factorial, okay? So plus n into n minus 1 into n minus 2, a to the power n minus 3, b to the power 3, all that on 3 factorial. And it continues until we have n factorial times b to the power n, all that on n factorial. So what will this give us? This will just give us b to the power n. And at the beginning, we'll just have a to the power n. So this is just equal to a to the power n plus n, a to the power n minus 1, b to the power 1, plus n into n minus 1 on 2, or we can write n combination 2 as we wrote before, a to the power n minus 2, b to the power 2, plus n combination 3, a to the power n minus 3, b to the power 3, plus all of this. So these are different ways in which you will find the binomial expansion being applied in different textbooks and in other manuals in which you find yourself. All these expansions mean the same thing. So you just have to stick on one, but if you stick on one, it does not mean if you meet another one, you will not know what to do. You should exactly know what to do. So let us recall the following combinations. N combination 0 is equal to n combination n, which is equal to 1. So n combination 0 has the same value as n combination n, and the value is equal to 1. Secondly, n combination 1 is the same as n combination n minus 1. And what does this value give us? This value gives us n. That is why at this position here, you find n, that's the second to the last term, and the second term also has n. Why? Because here we have n combination 1, the value is equal to n, and at the end here, we have n combination n minus 1 because the second to the last term, and the value is n. Equally, at the beginning, we have n combination 0, which is 1. That's why we just have 1 here, which has not been written. And at the end, we have n combination n, as you can see here, which is also equal to 1. That is why the term, the coefficient of b to the power n is 1. So this is what we observe. Let's take an example with the binomial expansion. Find the binomial expansion of the example given. We have 3 plus 2x to the power 4. Find the binomial expansion of 3 plus 2x to the power 4. So this will be equal to the first term. We have 3 to the power 4 plus, normally I always like it to write it like this downwards so that I don't make a mistake. So the next term will be the power. So we have 4 times, now this first term, this monomial, 3 to the power 4 minus 1, right, which is 3 to the power 3, in times, the second term here is 2x. 2x is now raised to the power 1. Recall that the sum of these powers must also always be equal to 1. So plus, the next term should be 4 into 4 minus 1. So I can write 4 combination 2. Okay, 4 combination 2 is the same as 4 into 4 minus 1, all that on the 2. So times, note that this first one here is n combination 0, which is 1. The second one is n combination 1, that is 4 combination 1, which is 4. This next term is 4 combination 2 into 3 to the power, which power now? 3 to the power 2 times 2x to the power what? 2, so that the sum is always equal to 4. All right, the next term now should be 4 combination 3. So 4 combination 3, and we know that 4 combination 3 has the same value as 4 combination 1, which is 4. So I can just write 4 instead of writing 4 combination 3, okay? So now 3 to the power 1, 2x to the power increases by 1 to the power 3. Then now plus the last term now, it should just be 2x to the power 4, right? Yeah, because this is going to give us n combination n. So here we have n combination 0, which is 1. Here we have n combination 1, that is 4 combination 1, which is 4. The next term is 4 combination 2, 4 combination 3, and this is 4 combination 4, but 4 combination 4 is equal to 1. And 3 to the power 0, because at this point you have 3 to the power 0, which is 1. So we are just left with 2 to the power 4. We can now simplify on a line, and we are going to have 3 plus 2x to the power 4 to be equal to 8. That's 81. 3 to the power 4 is 81. Plus 3 to the power 3 is 27 times 4. That gives us 216. That is 27 times 3 times 4 times 2. So we have 216x. The next one here, we have 4 combination 2 is equal to 4 times 3, which is 12. 12 times 9 times 2 to the power 2, which is 4. Simplifying that gives us 216 again. And the next term is, this one is going to be 4. 4 combination 3 is 4. So 4 times 3, which is 12 times 8. So 12 times 8 should give us 96. That's in this case now x cubed. And the last one is 16x to the power 4. So this is the binomial expansion of 3 plus 2x to the power 4. Another example, find in ascending powers of x the terms of this expansion. They want us to give the answer in ascending powers of x. So this will be equal to 2x. The first term is 2x, okay, to the power 5, recall. What's the next one? Know that this is n, that is 5 combination 0. So that's just equal to 1. And then now we have 2x to the power 5 times minus 1 to the power 0. Minus 1 to the power 0 is just 1. So the next term now will be 5. That is n combination 1. So we have 5 now times this term times 2x to the power, instead of 5 now 4, times minus 1 to the power 1. Yes, the sum of these powers must always be equal to 5. The next term now is 5 combination 2, right? Because this is 5 combination 0, 5 combination 1. The next one should be 5 combination 2. So 5 combination 2 into 2x to the power 3 into minus 1 to the power 2. The next term should be 5 combination 3 into 2x to the power 2 now, and minus 1 to the power 3, okay? Next term, 5 combination 4 into 2x to the power 1 and minus 1 to the power 4. The last term now should be 5 combination 5, which is just equal to 1. 2x to the power 0, which is still 1. 1 times 1 is 1. So times minus 1 to the power 5. So this is the expansion. So when we simplify, we are going to have 2 to the power 5 is 32, x to the power 5. And here we have 2 to the power 4 is 16, times 5, 80. 80 times minus 1 is minus 80x. We simplify these ones as well. 5 combination 2 times 2 to the power that will still give us 80x to the power 3. The next term is, and you see that it is alternating because of this negative 1. So if the power is even, then the term is positive. If it is odd, then it should be odd as well. So this is what we have as our answer, minus 1. But this answer is not complete because the question says in ascending powers of x. So at the end, you have to rearrange your work starting with minus 1. So your work now should start with minus 1 plus 10x minus 40x squared plus 80x cubed minus 8x to the power 4 plus 32x to the power 5. So you don't end here. I have deliberately ended here to emphasize on this. You don't end here because you have to follow the instruction of arranging your work in ascending powers of x. Now, we look also at the Pascal triangle. Guys, please, if you're watching this video, don't forget to click on the subscription button and equally click on the notifications bell, because without that, you'll not be notified immediately we upload a new video, which is going to help you. Don't forget to leave your comments down. Don't forget to share our videos. And of course, your comments are going to help us to look at other lessons. You can propose other lessons you'd like us to work on, and those be at your disposal. We are here to serve you. So as we're talking about the Pascal's triangle, it's another way of evaluating the binomial expansion. But what are the rules I gave before? The Pascal's triangle should be used when n is a natural number, and secondly, the value of n should not be large. For example, they should not give something like n to the power 10, or let me say 100 or 20, and you're using the Pascal's triangle. It is not going to be really good because it will be prone to errors. It's not as if it's wrong, but it will be prone to errors and it is time consuming. So what's the Pascal's triangle? The Pascal's triangle corresponds to the combination part of the expansion, that is n combination r. So it gives you, or it can replace the n combination r part of binomial expansion. So the Pascal's triangle is thus an alternative of n combination r in the binomial expansion. Note, however, that it is useful for lower values of n, as I mentioned above, and as n tends large, it is slow and prone to arithmetic errors. Now, let us see how we sketch the Pascal's triangle. So we always have to start with 1. And along these edges of this pyramid, or call it a triangle, these edges, all the values along this line are 1. Okay. So we have 1. Now the next value should be 1 again here and 1 at this position. So this is the base. This is where we begin. So this is the triangle, right? This small triangle. We keep on expanding this triangle and so on, depending on the power to which we want to work. So it depends on the power we want to end, n to the power 2, n to the power 3. And so if you have a binomial to the power 1, to the power 0, you end here. You start, you will just be this value. A binomial to the power 1, that means you should end here. Binomial to the power 2 should be the next line. And you're going to see 2 appearing. Okay. So we now add this 1 plus this 1 at this position is going to give us, can you see that? Some sort of dichotomy. 1 plus 1 gives us 2. So if you're working with x to the power 2, we should be at this position. Then we put 1 at these positions to complete the triangle. So if I'm working with a plus b to the power 2, then my Pascal's triangle should end here. For example, if you have to expand a plus b to the power 2, it's going to give you a squared, that is 1a squared, which corresponds to this 1, plus 2ab, this is the 2, this is the coefficient, then plus b squared, this is it. The Pascal's triangle gives you that. If you have to go to x cubed, let us look. To consider this triangle, we have 1 plus 2 at this position. So we have this dichotomy, that gives us 3. And equally here, we have 1 plus 2 again, that still gives us 3. And then, of course, we place 1s at these ends. So if I'm trying to expand something like a plus b, all raised to the power 3, then you should give me a cubed plus maybe a plus 3a squared b plus 3ab squared plus 1a cubed. So this is going to give us, the Pascal's triangle is going to give us this value if I expand, which you can equally use combinations. So if I have to go to powers like 4, then I'll have 3 plus 3, this gives me 6. And 3 plus 1 gives me 4 at this position. 1 plus 3 equally gives me 4 at this position. And of course, 1 at these ends. So if I have to expand anything like a plus b to the power n, these are going to be the coefficients. Then what about the power 5? I continue my dichotomy. 6 plus 4 is 10. 4 plus 6 is 10 again. This position 1 plus 4 is 5. And 1 plus 4 is 5. And of course, we place 1 at the ends. This triangle continues. If I have to expand, so this one is telling me it's to the power 5, this line, to the power 4, this line, to the power 3, this line, to the power 2, this line, to the power 1, this line, to the power 0, this first point here. If I have to continue to the power 6, then I have to, my 6 should indicate here. So advice, we use the Pascal's triangle again if n is a natural number. Let us look at an example here. So, and correspondence, n combination r in triangle. So in this first part, if you have a plus b all squared, these are going to be the coefficients when you expand. This replaces the n combination, whatever. If you have to go with a plus b to the power 3, this gives us the coefficients of the terms that we are going to have. Then, if we have a plus b to the power 4, these are the coefficients we are going to have. And of course, a plus b to the power 5, and it continues a plus b to the power 6, a plus b to the power 7, and so on. Let's take an example. Using the Pascal's triangle, find the expansion of the binomial x minus 2 raised to the power 3 using the Pascal's triangle. So let's see how we're going to apply the Pascal's triangle to find this expansion. So since I'm at the power 3, I have to move up to this point. Can you see these are the 3 here at the end now? So immediately after 1, I have 3. Immediately after 1, I have 3. So these are the coefficients I will have the expansion of x minus 2 to the power 3. So I'll just write my terms out. X minus 2 to the power 3 should equal to x cubed. That this should be 1x cubed. Then the next one should be x squared. Normally, the second position now will be x to the power 2, 3 minus 1, which is x to the power 2. This next term now, the power is increasing by 1, such that the sum of these two parts is always equal to 1. So now have x to the power 1 and minus 2 to the power 2. And the last one should just be equal to minus 2 to the power 3. So now I need the coefficients. The Pascal's triangle is going to give me these coefficients. From here, my coefficients are 1, 3, 3, 1. So this first position should be 1. This second position should be this 3. The next position should be this 3. And the last position, of course, is plus 1. So this is how we apply the Pascal's triangle. I can now simplify. I'll have x cubed plus, the next one is x squared. And what's going to be negative 6x squared plus 12x minus 8. So this is how I apply the Pascal's triangle for expansions. Now find the first n terms and maybe in ascending or descending order. So how you can find the first n terms of a binomial expansion. To find the first n terms, please don't forget to subscribe and to leave your comments. Thank you so much. Your comments are going to help us so much to improve on the qualities of our videos. If I'm speaking very fast, of course, you can click on the speed button on this YouTube video that is playing and reduce the speed maybe to 0.75, and I will speak at your pace. Thank you so much and stay tuned. So example 4, find the first 3 terms of the binomial using Pascal's triangle in ascending powers of x. With this particular example, they want us to find the first n terms, and they said in ascending powers. So they don't want the first terms in descending powers. Let us see a trick here. We have 2x plus 3 to the power 4. Normally, if I expand this, like we saw in the previous example, these powers are going to be x to the power 4, x to the power 3, x to the power 2, that. And what happens, I observe that my answers are going to be in descending powers of x. That is going to slow me down. So I'm going to do some tricks here. What is the trick? I will make sure that I swap the positions because addition is commutative. I will now write this as 3 plus 2x to the power 4. Can you see? So that when I just do the expansion at once, I will have my answers in ascending powers of x. Because many students will take it directly like this and they'll give their answers in descending powers of x and they will not realize that it is wrong. So this question is tricky. And that's why I started with this one. So this is my Pascal's triangle, which I'm going to use. I need only the first 3 terms. And I've decided to write this as 3 plus 2x to the power 4. So the coefficient of the first term should be 1, the second term should be 4, and the next one should be 6. I should end at that point. So this is going to give me 3 plus 2x to the power 4 to be approximately equal to, because I need just the first 3 terms, to be approximately equal to the first term. So I have 3 to the power 4. Now the next one should be 3 to the power 3, the power reduces by 1, and then 2x to the power 1. 3 to the power 3, 2x to the power 1. And the last term, because I need just the first 3, should be 3 to the power 2 and 2x to the power 2, right? Now let me get my coefficients from here and feed them directly. I have 1, 4, 6. So this gives me, this first one is 1. There's no need to write it. The next one is 4, and the last one is 6. Now we simplify, we'll have 81 plus 216x plus 216x squared, and so on. So can you now see that you have in ascending powers of x, this x to the power 0, here x to the power 1, and here x to the power 2. If I did not do this adjustment, what would have become of my answer? My answer would have been coming from this direction backwards, which will not match with the instructions. Take note. Let's take another example. That's the example is direct in this case. Find the first three terms of the binomial using Pascal's triangle in ascending powers of x. I am using Pascal's triangle because this question emphasizes on Pascal's triangle. Otherwise, I will use my combination direct. So here I have this 5 plus 2x to the power 9, which is approximately equal to. Now, this one's arranged in such a way that my answers will just come out in the ascending powers of x. You can see that the x occupies the second position in this expression, not the first. So it's going to give me answers in ascending powers of x. So this is going to give us 5 to the power 9 plus 9 into 5 to the power 8 and 2x to the power 1. So plus 9 into 9 minus 1, all that on 2. So we can write 9 combination 2. Okay, so use Pascal triangle. Okay, I've just decided not to use it here. I'm sorry about that, but so 9 combination 2, 5 to the power 7, 2x to the power what? 2x to the power 2. And that continues. So this gives me approximately 1,953,125 plus 7,031,250x plus 11,250,000x squared. And that's it for that question. Don't forget to subscribe and to leave your comments below. We're going to trash this video to the end. Example 6, find the first four terms of this binomial expansion in ascending powers of x. So the first thing I observe here is that the constant is coming before the term in x. So obviously, if I expand, my answers are going to be in ascending powers directly. Otherwise, if the x occupying the first position, then I expect my answers to be in descending powers of x. But at this point, as the question is given, it's going to be in ascending powers. So here they have not specified about Pascal's triangle or whatever. So I can do it using my combinations. So this would be approximately equal to, the first term is 2 to the power 6 plus 6 into 2 to the power 5 minus 3 to the power 1 plus 6 combination 2, 2x to the power 4 into minus 3 to the power 2. And we have 6 combination 3 into 2 to the power 3 minus 3x to the power 3. And when we simplify, this is what you obtain at the end. And I equally advise you that as you watch this video, it's also very good that you solve, because if you just watch the video without solving, then you are not doing yourself any good to gain the skills. Don't forget to subscribe and to share our videos in your WhatsApp groups, on Facebook, on Twitter, and all other platforms in which you find yourself. That's going to be the way in which you encourage us in creating more quality content for you, and also propose the type of content you like us to put up. Finding the coefficient of a given term. To find the coefficient of a given term. Let's take an example. Find the coefficient of x to the power 6 in the expansion 3 plus 2x to the power 8. To find the coefficient of the term with x to the power 6 in this expansion. So of course, I will know this term to the power 6. We are going to use a shortcut. You're not supposed to do all of it, okay? So how do we start to answer this type of equation? So look at it. We first of all start with this 2x. Since it's just 2x, means if I raise this to the power 6, it's going to give me 2x, it's going to give me x to the power 6, okay? Some sort of. So this is going to give me x to the power 6, no matter what I do. So I start with this. This is going to give me x to the power 6. Now, the next one should be this term in front, this term 3. So if this is 6, then I should have 3 to the power 2, so that the sum of these two parts should be 8, right? Okay, so now I have 3, and this 3 must raise to the power 2, so that the sum of these two parts should be equal to 8. Now, what I have to put in front now is the combination. It should be the combination. And I made mention of something about the combination before, which we are going to see. So our n here is 8. Our n here is 8, right? So I have 8 combination. So combination, what number? That is the number now that is very, very important here. Let's see what we have. Combination 6. Recall, I said this number at this end here must always correspond with the number at this position. So this is going to give me the coefficient of x squared. Now let us expand and see what we have. So this is going to give us 16,128x to the power 6. So what is the coefficient of x to the power 6? It is 16,128. So this is just a short trick to find the coefficient of x to the power 6 in this expansion, as sweet and simple as it is. Now, solving for an unknown. Solving for an unknown, this is now a high level problem. So how do we solve for an unknown in a binomial? So example, the coefficient of x to the power 3 in this expansion of p plus 2x to the power 5 is 2000. Find the value of p given that p is greater than 0. So you're being told that the coefficient of this x to the power 3 is 2000. Of course, from example 7, we know how to find the coefficient of x to the power 3, okay? So let's see how we find this coefficient. So the coefficient here is going to be, we start with this 2x, right? And it should be to the power 3, so 2x to the power 3. The next one is this p now. So I'm going to have p to a certain power. The power of p must be 2 because the sum of these powers must be equal to 5. Now with the combination, I should have 5 combination. Which number should correspond to this one, right? So we should have 5 combination 3. So now this is going to give us 80p squared. 80p squared x cubed. So the coefficient of x cubed is 80p squared. And we are being told that this coefficient is equal to 2000. So we now see that 80p squared should be equal to 2000 according to the equation. And from here, p squared is equal to 25. And since p must be a positive number according to the equation, p must be greater than 0. So p is equal to 5. This is a very, very nice example. So p is equal to 5. So here we have an exercise, and please, we will call on you guys to solve this exercise. You can leave your comments after solving below. Okay, evaluate 4 factorial, the answer is there. 5 combination 2 is 10, combination 3 is 20. Now find the coefficients of x squared in these expansions. If you go through this video, I cannot answer all of these questions. It means you have to go through the video again. You have not actually learned everything. All these exercises here are exactly examples, or are exactly from the examples we have done. So if you have gone through the lesson very well, then you should be able to answer all of these questions as fast as possible without any hindrances. So that brings us to the end of part 1. That part 1 is very important. If you're doing additional math, if you're doing pure math, or you're doing further math, that first part is for all of you. But this second part is mostly for advanced levels and for those who are doing further mathematics. So first, this second part is for advanced level only. But all of that first part is part of advanced level as well. So this is where we end for the first part, and please go to part 2. Hello guys, and welcome to part 2 of the binomial expansion. This general binomial expansion applies to other types of pairs. Remember that in part 1, as we just mentioned, unlike working only with n being an element of the set of natural numbers, this general binomial expansion works with all pairs. It does not care about whatever value of n you put in. And the general form is written as 1 plus x to the power n is equal to 1. The coefficient here is 1 normally. So 1 plus nx plus n into n minus 1 on 2 factorial x squared plus n into n minus 1 n minus 2 on 3 factorial x cubed, and it continues. So normally, like with the first case, if n is a natural number, we find out that we have a finite number of elements. However, if n is not a natural, then we might end up with an infinite number of terms in the series. So remarks, fractions and negative n values are also applicable in this particular case. So here we can work with fractions and negative values of n, unlike the previous. Right, so so this is what we have for this general expansion, and with this expansion, the absolute value of x should be strictly less than 1. This is what we call the validity, which we are going to talk about equally in this video. So if you have 1 plus x to the power n, it can be written in this form, and the absolute value of x should be strictly less than 1. The size of x is less than 1, so raised to any power, it is close to 0. Please take note of this. The absolute value, that's the value of x, should be less than 1. You know that any number that lies between -1 and +1, when you raise that power to that number to a very high power like infinity, the value is equal to 0. You can test on a calculator. Just take, for example, 0.5 to the power infinity or to the power 10,000. It becomes approximately equal to 0. So unless n is a natural number, the expansion, like I previously mentioned, is infinitely long. So it's only valued for the absolute value of n less than 1. Absolute value of n means n lies from -1 to 1. So this is what we call the validity statement. This restriction means the series will converge. So if the absolute value of of x lies between -1 and 1, or strictly less than 1, that's the absolute value strictly less than 1, it means the series will converge. That's what we call the validity statement. Therefore means that higher powers of x can be ignored. Okay, x to the power r as r turns to infinity is approximately equal to 0. In this case, only the first few terms of the expansion may be needed to give an estimate or an approximation to any value, which we are going to see in examples in this particular lesson. So let's take an example. Example 11, we have expand 1 plus x to the power a half and state the range of values of x for which this expansion is valid. So this one is direct. 1 plus x to the power a half should just be equal to, you have 1, the first term is 1. So now plus n, n is a half. So plus a half x plus a half into a half minus 1. That is minus a half x squared, all that on something, all that on 2. On 2 factorial. I know that this first one is on 0 factorial. This one is on 1 factorial, this one on 2 factorial, but 0 factorial is 1. 1 factorial is 1, so we don't have time to write in all of that. That's why from the third term, we put in the 2 factorial. Now, the next term is going to be a half into minus a half minus a half again. What does that give us? Minus 1. Minus a half minus 1 gives us minus 3 on 2. In this case now, x cubed, all this on how many factorial? 3 factorial. Okay, note that the factorial, the value of the factorial must always correspond to the power of x. So here we have x to the power 2 on 2 factorial. Here's x to the power 1 on 1 factorial. Here's x to the power 0 on 0 factorial. So this one continues plus, plus, plus. So this is approximately going to be equal to, normally the first 4 or 5 terms is where they always end. You cannot give everything. Okay, so you have to take note of that. So this will be equal to 1 plus you have x minus 1 over 8 x squared plus 1 over 16 x to the power 3 and so on. So this expansion is valid. So what's the absolute value here? At this position, we have x, right? When we have 1 plus any number, the absolute value of this number should be less than 1. So it's valid for the absolute value of x less than 1. So it is rare to go beyond x to the power 5. It is rare. You hardly see equations that go beyond. Even to the power 4 is really rare too. Example 11, find the first 3 terms of the expansion 1 over 1 minus x. 1 over 1 minus x. Someone now will be tempted to say that, but you have not done this type. What you have to do here is start by saying this one is equal to 1 over 1 minus x to the power a half. But 1 over 1 minus x to the power a half is the same as x to the power 1, that is the same as 1 minus x to the power minus a half. So here we have, this one is the same as 1 minus x, all this to the power minus a half. And we can now do our expansion directly. So this is going to give us 1 plus, the power now is minus a half, so plus minus a half into this term now, minus x plus, we have minus a half into minus a half minus 1, which is minus 3 on 2. Okay, into minus 3 on 2. And the next one here is minus x squared, all this on 2 factorial. All right, take note of this. This is not 9. This is bracket. Trying to put a bracket here. Sorry. So this is a bracket. So we continue. So plus that it continues and so on. But the one, just the first 3 terms. So this is going to be equal to 1 plus a half x plus a half x, and the next term is plus 3 over 8x squared. So these are the first 3 terms of this expansion. And what is the validity? It is valid if, so we already have it in the general form, which is 1 minus x. So this the absolute value of this minus x should be less than 1. Therefore, it's valid for absolute value of x less than 1, because the absolute value of minus x just gives us x, right? So it is valid for x strictly greater than -1 and strictly less than 1. That's what this statement means. Okay, so the next example that we have here, which is also direct, the next example, find up to the term x squared in the ascending part of x. B, write down the values of x for which the expansion is valid. So this expansion we have, the first thing is to find up to the term containing x squared, okay? So we can write this as 3 into 1 minus 2 on 3x to the power minus 2. So this can be written as 3 into, at this position, 1 minus 2 over 3x to the power minus 2. Okay. And from here now, we just have 3 with the bigger brackets outside. You have 1, this term now, plus the power minus 2 into minus 2 on 3x at this position, plus minus 2 into, this is minus 2 into minus 2 minus 1 is minus 3. All that on 2 factorial, 2 factorial is 2 times now minus 2 on 3x squared. Now this second part of the term is minus 2 on 3x squared, and so on. So we have arrived at the term containing x squared, so we have to end here. All we have to do now is just to expand the brackets and simplify. So this gives us 3 into 1 plus 4 on 3x plus 4 on 3x squared, and so on. So the term up to the term containing x squared, this will be approximately equal to, so we completely expand this bracket, so we have 3 plus 4x plus x squared. So what are the values of x for which this is valid? So for the validity, we look at this position here. We already have in the form 1 minus 2 over x to the power 3. So this minus 2 over 3 x minus 2 over 3, absolute value of minus 2 over 3x should be less than 1. And when we solve here, we're going to have absolute value of x to be less than 3 on 2. So if you bring out this minus 3 on 2 from the absolute value, you have 2 over 3. Then multiply both sides by 3 on 2. You'll be left with absolute value of x is less than 3 on 2. So this example looks frightening, but it's a very simple example. You just need to solve more. Note that a plus b to the power n is the same as, so if this number here is not 1, this is what I want to emphasize now. If this value is not equal to 1, see what you can do to make it look as the general binomial expansion. So you can factor out this a to the power n. So this will become, we have 1 plus b on a. I'm starting with this. I'll divide all through by a. So I'll have 1 plus b on a. I put my brackets, okay, brackets. Then now, so this a is outside. I factor out the a, right? So the a is at that position. So this is what I have in this bracket. If I raise everything now to the power n, this will give me a to the power n, a to the power n. So I can do like this, and I'll now have the term in this form. So this is the general binomial expansion which we see. Whenever we have complex operations to simplify, we convert to this general form and we do the simplification. Take note of this. So this can now be easily used for the general expansion and is valid for the absolute value of this b over a to be less than 1. This is the validity now statement for this. So let's take an example. Find up to the term x squared in ascending powers of x for this expansion and write down the value of x for which the expansion is valid. So this one is the same as 1 over 8 minus 3x, all this is the power 1/3, which is equal to 8 minus 3x, all that's the power minus 1/3. This is it. So expand, it will become 8 minus 3, all that is the power minus 1/3. Now it is not in the general form, so I have to factor out this 8. When you factor out this 8, I'll be left with 8 into 1 minus 3 on 8x, all that's the power minus 1/3. Now this is the same as 8 to the power minus 1/3 into 1 minus 3 over 8x, the power minus 1/3. So this is what I have. This is the first step. So this is my first step. I can now expand this 1 minus 3 over 8x to the power minus 1/3 using the binomial expansion. So this gives me 1 plus, the power is minus 1 on 3 into minus 1 on 3 minus 1 is going to give us for this next one should give us minus 4 on 3 on 2 factorial, minus 3 on 8x to the power 2. So when we simplify, this is what we are going to have. And finally, since they need just the term up to the term with x squared, we have approximately a half plus 1 over 16x plus 1 over 64x squared at the end. And note that the cube root of 8 is 2. So this term here becomes 1 over 2 into all of this. So what is the validity for this expansion? To get the validity, let us come back to this form here. So we have 1, this is the general binomial expansion form, 1 minus 3 over 8x. So this minus 3 over 8x, the absolute value should be less than 1. So the absolute value of that should be less than 1. Okay, so minus 3 over 8x, absolute value should be less than 1, and x should be less than, that's the absolute value of x should be less than 8 on 3. So you can write it as minus 1 over 8 should be less than x less than 8 on 3. Okay, now find the binomial expansion of this one up to the term including x to the power 3 and state the value of x for which this expansion is valid. With this one, just like the previous case, we just have a product. So the first thing, we arrange the first one, the numerator as 1 plus x to the power a half. And what becomes of the denominator? It becomes 3 plus 2x to the power minus 1. This is it here. Okay, now we expand each of them separately. We have to end with the term in x cubed. So I'll expand each and end with the term in x cubed. So for the first one, I have 1 plus x to the power a half will be equal to 1 plus a half x plus a half into a half minus 1, which is minus a half on 2 factorial x squared, plus a half into a half minus 1, which is minus a half minus 2, which is minus 3 on 2, all that on 3 factorial, which is 6x cubed. So I'll end here with the first one. And this first one is going to give me 1 plus a half x minus 1 over 8x squared plus 1 over 16x cubed. Now for the second, this is what we have. The second, we have this. We first of all start by writing in the general form of the binomial. So this gives us, we factor out these 3. It becomes 3 to the power minus 1 into 1 plus 2 over x, all that is the power minus 1. Okay. So the next step now, we expand. When we expand it, we are going to have 1 over 3 into 1, the power is minus 1 into 2 over 3x plus minus 1 into minus 2 on 2 factorial times 2 over 3x to the power 2. Then the next term should be minus 1 into minus 2 into minus 3, all that on 3 factorial into 2 over 3 x to the power 3. And we simplify it. When we simplify this, what we have. Now we know that the root of 1 plus x over 3 plus 2x is equal to the product of these two. That is what we have at this position here. So we are going to multiply what we have for this first expansion by what you have in the second expansion. So we have this times this. So when we expand, any term that when we multiply, the value is more than x cubed, we leave it out because you don't need it. So we have 1 times 1 over 3 is 1 over 3. 1 times 2 over 9x is 2 over 9x. 1 times all of this up to this point is what we have. Now a half x times 1 over 3 is 1 over 6x. This second line is for this a half x times this second bracket. The third line is for this minus 1 over 8x squared times this bracket. Like for this third line, minus 1 over 8x squared times 1 over 3 is minus 1 over 24x squared. Minus 1 over 8x squared times minus 2 over 9x is plus 1 over 36x cubed. But minus 1 over 8x squared times 4 over 27x to the power 4. This is going to give me a term that's above x to the power 3. So I will not take that one. I have to stop. I now take 1 over 16x to the power 3, and I multiply only by this first one. Because if I multiply by the second, I'll go to x to the power 4. So that's why these lines look like this. And we can now add these terms together. And this is the result that we have at the end. This question is a very, very important question, and it repeats in so many past questions. So you have to take note of this type of settings. Those doing especially additional mathematics, they'll find this very important. For those doing just mathematics, they might find this expansion, but they might just end at looking at some few values on arrangements and so on. So the general binomial expansion, we have a root of 1 of 1 plus x, it can be arranged as 1 plus x to the power a half and valid for absolute value of x less than 1. For this second case, it is valid for, you first of all arrange it in the general form, and you have 2 over 3x, absolute value of that should be less than 1. And it will be valid for absolute value of x less than 3 on 2. So it's always very important to give the validity of an expansion, even if they might not have asked for it. Okay. All right, now let's look at this. For this expansion, they want us to find the binomial expansion of this up to the term including x squared. With this particular case, what I want to emphasize here is you have to, first of all, express this in partial fractions. This one is very important. You first of all express this in partial fractions, and expressing this in partial fraction will give us 2 over x plus 4 plus 3 over 3x minus 1. You arrange it now in the general form. Can you see? So this expansion at the end is going to be this expansion plus this expansion. Expanding the first will give us these values. Take note of this page. Will give us a half into minus 1 over 8x plus 1 over 32x squared. These guys, for these notes, you can go to our website, www.gcemathspanel.blogspot.com or gcepreps.blogspot.com, where you can get these notes. If you cannot get this, then you try gcemathspanel.com or gcepreps.com, where you get these notes. And you take note that for the second one, equally 3 into 3x minus 1, or raised to the power minus 1. When we expand this, what we are going to have. So at the end now, we have to add these 2, because they need only the first term, the terms up to x squared. So I'm going to add these terms with x squared. And adding all of this is going to give us minus 3 minus 9x minus 27x squared. So for the addition, we add these 2, this for the second case, and for the first case, we add this and we arrive at our answer. So for the values for which this expansion is valid, this is what we need to do. We have to check the validity of this first part and validity of the second part. The intersection of the 2 validities is going to give us the actual validity of expansion. Okay, so like the first one, it is valid from -4 to +4, but the second is valid from -1 on 3 to +1 on 3. So what is the intersection? Intersection is -1 on 3 to +1 on 3. So we take the intersection, which is the absolute value of x should be less than 1/3. That's the validity that we are going to consider. Okay. Now find up to the term in x squared in ascending powers of x for this expansion. And be write on the value of x for which the expansion is valid. So let's see what we do with this one. So this one can be broken down to numerator times denominator in this form. So I'm just emphasizing on what to do now. So we have 1 minus x to the power 1/3 into 1 plus 2x to the power minus 1/3. We are going to expand this part, which gives us 1 minus 3x squared minus 3x minus 1 over 9x squared, because they have to end with the term in x squared. So I end there. And the second one, I also end the term in x squared. And at the end now, I have to multiply this first answer by the second answer while eliminating terms which are having values greater than x squared. And this is the final result that we have. So at the end, we have 1 minus x plus x squared. And what is the validity? This first part is valid for x lying from -1 to +1, while the second is valid for x lying from -1/2 to +1/2. The intersection is from -1/2 to +1/2. So that's the validity which we are going to consider. All right, guys, please, if you have any concerns with this video, you can watch and rewatch. And if you have any issues, why not leave your comments in the comment section below or join us. So here is our validity, as I explained. It is valid from -1/2 to +1/2. So we look for the intersection of the validities of 1 minus x to the power 1/3 and the validity of 1 plus 2x to the power minus 1/3. The intersection of these 2 validities gives us the validity of the expansion. So the second to the last part of the video is about approximating values. Sometimes you may be asked to compare, to find an approximate value of an expansion, the numerical expansion. For example, use the first 3 terms of 1 minus x squared to find an approximate expansion to 0.96, the root. Okay, so if I expand 1 minus x, I'll start by, first of all, and I approximate 1 minus x to the power a half should be equal to what they have given me here. So at this, if I compare coefficients, 1 minus x should be equal to 0.96. And what is x? X will be 0.04. Now, whenever you're asked to approximate, you can use just the up to the term in x squared. You can always end with the term in x squared. If I expand 1 minus x to the power a half, what does that give me? It gives me 1 minus a half x minus 1 over 8x squared. But from this expansion, what's the value of my x? My x is equal to 0.04. I now substitute these values here, and the expansion gives me 0.9798. So this is how we approximate, whether they've given you trigonometric functions or what type of functions. The first thing, take the approximation I've given, like root of 0.96, and equates to root of 1 minus x. Solve for x. What's the x value? Now find the approximate of this expansion up to the term in x squared. When you have that expansion, substitute this value of x, and that will give you the estimate or approximate of that, whatever they're looking for. So equally here, find the term including x squared in the binomial expansion of this, and then B, use your expansion in A to find an approximate of the fourth root of 85. Explain why expansion will not be suitable for the fourth root of 171. So let us see. So here we equate fourth roots to fourth roots. So root 81 minus 9x should be approximately equal to 81 to the power 4 into 1 minus 9, 1 over 9x to the power 1/4. So if I expand this, this is what I'm going to have when I expand. Now here I have the fourth root of 85. So let me see what I'm going to do. So here the fourth root of 85 is approximately equal to the fourth root of 81 minus 9x. We equate coefficients, and you see that x is going to be 4 or 9. I now take this x squared minus 4 or 9 and substitute in the previous expansion that I had and simplify. When I substitute and simplify, this is the result that I'm going to obtain after simplifying and doing that. All right, let's now explain why your expansion will not be suitable for approximating the root of 171. Why will it not be suitable? So, like we say, this is a well-hidden question about validity. This is a well-hidden question about validity. Now, let's see something. I have to first of all start by equating what they have in the equation to this, the fourth root of 171. I solve for x. Now, what is the value of x that we have here? Is minus 10. But what is the validity of this expansion? Let us see. X should only lie from -9 to +9. Can you see something here? But this value of x is equal to -10, which lies outside the validity range. Therefore, the approximation will not be valid. So the expansion is not valid when x equals -10. And so the fourth root of 171 cannot be approximated. This is a very, very, very important tough question. It's always hidden. It's a very important question. The tough one. So find the term independent of x in the expansion of this. So if for a plus b to the power n, we have x to the power n in the first monomial, and x to the power n the second monomial, then we'll end up having a term independent of x. In the previous examples, we usually have terms independent of x, but these are special cases. So to find the term independent of x, we see that let that term be the r plus 1 term. So n combination r, a to the power n minus r, b to the power r is what we solve for. We look for this and equate to x to the power 0. So this will give us 6 combination r, x squared into 6 minus r. That's for this expansion. Okay. So this x squared into the power is 6 minus r. This other term is 1 over 2x, 1 over 2x to the power r. We simplify. So it's going to give us 6 combination r times 2 to the power negative r times x to the power 12 minus 2r minus r. So that gives us x to the power 12 minus 2r minus r should be equal to x to the power 0. Why are we equating to the power to x to the power 0? Because this is the term that is going to be independent of x. The term independent of x is that term that has x to the power 0. So here we now solve for x, And we see that we solve for r, and the value of r is going to be 4. Therefore, that term independent of r is going to be the r plus 1 term. It's going to be the r plus 1 term. Okay. Since our r is equal to 4, that term independent of x should be the 5th term. And that is going to be given by this part of this combination that we have here. 6 combination r times 2 to the power negative r. So you have 6 combination 4 times 2 to the power negative 4, which is 5 on 4. I have just this one example here, but there are many examples out there. They all follow the same procedure. However, if n is small, you can still expand to find term independent of x, but it's going to waste your time. So our next lessons are going to be arithmetic and geometric progressions. Guys, don't forget to join us, subscribe to our channel, and much is still to come. We equally have videos on math mechanics and math statistics. You will find pulley systems. You will find different types of levers and many other examples on probability, statistics, and all different types of values in mathematics. Thank you so much, and don't forget to subscribe and to leave your comments. Bye-bye.